Hello everyone, welcome to Lab 4. In this lab, we are going to discuss the Gaussian elimination method to solve a system of linear algebraic equations. Gaussian elimination is a direct method since it doesn't involve any iteration. Here, as you can see, there are n numbers of linear algebraic equations, which is also termed as a system of equations. The important aspect of this system of algebraic equations is we can arrange them in a nicely organized matrix and solve for the unknown variables efficiently in MATLAB. Here, the constant coefficients can form a matrix which is represented as Aij. Then the unknown parameters or the variables can form another matrix that is represented as Xij. And finally, the constant or the non-homogeneous term at the right side of the equation can be represented by another matrix, Bi. So I stands for the row and J stands for the column. And in short, we can represent the equations as Ax equals to B. Gaussian elimination involves two steps. First is forward elimination and then backward substitution. Forward elimination has three steps. Scaling, which is multiplication of a row by a constant. Then pivoting, which is basically interchanging the order of any rows. And final step is elimination, which means that any row can be replaced by a weighted linear combination of that row with any other row. Once we are done with these operations, the matrix should look like this. All the coefficients under the major diagonal are 0. There is a general formula for this elimination process, which you can see here, but I will explain it in the next slide with an example. Backward substitution is pretty simple and straightforward. From this matrix, we know the unknown parameters for the last equation, and we then substitute it to the above equation and so on to get all the parameter values. Back substitution also has a general formula like this, like the forward elimination. In this example, we see three algebraic equations. Our first task is to write it in a matrix form, which is done here. Next, we merge B matrix into the coefficient matrix A, which is a process known as matrix augmentation. Then, according to the forward elimination, select column 1, and search for the largest element, which is 80 here in this example. We want to get rid of minus 20 in the first column by dividing 80, which is a pivot element in this case. We are multiplying the first row with the elimination multiplier, minus 20 over 80, and then subtracting it from the second and third row to eliminate 20x1. So after that, we see the first column has 0 elements below this major diagonal element. Next, we select column 2 and search for again the largest element and do the same process. So after that, we end up with this matrix, and we see below the major diagonal all the elements are 0. So we can start the back substitution process. So the first start with the last equation. So the last equation is this one. So from that relation, we can find the parameter x3, then substitute it in the previous equation. We can get the parameter value x2 and then x1. We will code the Gaussian elimination algorithm by MATLAB. Uh, Before coding, I want to discuss the vectorization in MATLAB. On the left side, you see a typical for loop operation to evaluate cosine t for the defined range. On the right, we have a vectorized version of the same loop, which is shorter to write and faster in terms of MATLAB computation. Now let's see detailed codes in MATLAB. I wrote this program to implement Gaussian algorithm. This is a generic code which has the scaling and pivoting features. We need these features if, for example, your first coefficient in the matrix is 0. So in that case, this is necessary. So our example doesn't have that, but you'll find some examples which will have that 0 elements. So in that case, the partial pivoting and scaling is necessary. The function name here is Gauss elimination, which is two inputs, A and B. So as you see here, A is a n by n matrix or a square matrix which has the same number of column and rows, and B a column vector of length n. So our first task, we have to define these two matrices A and B. So what is here we are doing, so M actually it will give you the number of rows in a matrix A. So actually we know the matrix, our input matrix A and B. So what we are doing, we are just extracting the size, number of rows for A matrix, and now the length for B matrix. So why we are doing this, we have to make sure whether these numbers, the number of rows in A and B, are same or not. If they are not same, so the program will terminate immediately, because this is a limitation for Gaussian elimination. I mean, if that are not same, the number of rows in A and B matrices are not same, so the program actually, there is no point to continue our calculations, so the program will immediately stop here. But if this is actually I mean satisfied, I mean, like we have same number of rows for both A and B, then we can continue. So the first step is augmenting the matrix. That means we have to merge the matrix B into A. So by this line here, you see we are actually doing the same thing. Now here I am defining two for loops. So first for loop is for the column 1 until n, and then the second for loop is for the row. So there are actually two loops here. So for the first loop, for the column loop, so we are doing the scanning here. So what is a scanning actually? So we need to look for the maximum magnitude of an element in a column and then divide that. So we are doing that here, and after the normalization is done, so we are just storing that parameter in a temporary matrix, in a different matrix here. Next, we will switch the rows. So here you see how we are doing the switching. So for for this matrix A, for the new matrix, we are just flipping between two rows. So CF, and in the new our row, which is FC. So just take a look how we write the codes, and this is actually uh, a shorter version of writing. So we are considering this matrix A, and all the elements in this matrix, they are keep updating continuously in this loop. So just be careful when you are defining this. Now we are actually defining another for loop for the diagonal elements. So this line here is actually the elimination multiplier I just showed for the example there. So it stores the elimination multiplier, and which is actually implemented in the next loop to get rid of all the elements below the major diagonal. So this is that line. So this line actually, what it does, it actually makes the uh, elements zero below the major diagonal for each subsequent column. So it starts with for first column, and it will continue until you have reached column n. So, and when you are done with that, so this loop will end. So we will also end this loop here, and uh, another which we begin for this row and uh, column loop. So when we are done with this process, next our task is back substitutions, and the back substitution is generally pretty straightforward. So we have to begin with the last actually equation. So for the last equation, we know the value of the unknown parameter. So the loop will begin from the second last, that's why n minus 1, and we are actually deducting 1 because we are going upward, we are going in the back directions subsequently. And by this line here, actually we are implementing that generic formula here. So in MATLAB here, actually, this writing, defining your matrices or arrays with the variables. So here the variable is j or a. So it's very convenient. So just be careful when you are defining the dimensions of the matrix. So here actually when you are considering this a jn plus 1, so it actually refers to the element of our matrix A, so which is, for our example, is a 3 by 3 matrix, and it actually defines the element number, which element, so specifically it is defining. And for this column here, for I until n plus 1, so how many actually columns it will take. So that means this array is a variable. I mean, it is keep updating every time. So uh, it's an interesting feature, but also sometimes make you confused. So just be careful with that. So and like when you are done with this back substitutions, you will have all the unknown parameters, and the program will end here. So let's see for our example what we have for the A matrix. So these are just the coefficients of the matrices I have defined. So A matrix, which is stored in our workplace, and our B matrix, which is pretty simple, 20, 20, 20. So now A and B is defined. So what this program will do first, it will take the length of A and B and compare if the number of rows are same. So it is same here, and this example is very straightforward. So it will actually jump into the calculation for the elimination multiplier and then do the rest of the process. So now we will call this function Gaussian elimination A and B, and let's see how it does. So you see here we have the same outputs like what we have done for our manual calculations. So our program actually is correct. So the results are same. We can verify that. Now let's say we have polynomial equations. We discussed earlier with the system of linear algebraic equations. Now what about system of polynomial equations? We can do it similarly. Here you see we have a polynomial series, and if we split up, we have n number of polynomial equations. Now let's say here the uh, coefficients here are not known. That means a0, a1, a2, they are unknown, and we know the parameters for the polynomials. We can actually form the matrix in the same fashion, but just be careful here. For this series, you see if this a are variables, so the first coefficient element is always 1. That means your first column will be 1. And next, in the same way, you can actually place all other elements. Now you may end up with few data points in some cases for plottings that might not give you a smooth nice curve. In that case, if you would like to create a smooth plot, you can actually follow this approach. Let's say xplot is the array having fewer data points. You need to just take line space with a maximum and minimum value of your data points, which will give you eventually 100 equally distant data points. Then generate another array which is yplot with the same dimensions. Then write a simple for loop and plot with this new data